we move now to uniform consensus. So let us look to the description of the previous algorithm, not using event-based notation, but control-oriented notations. So let us try to understand this control-oriented notation. So a process will run code very much like languages like Erlang, and they can send messages and receive messages. So let us see how these work out. So let us look to process PI. And so process PI has its initial proposal here. And for each process, of course, execute this code. So for R from 1 to n, the number of processes, if I am in round I, it means I am the leader. Then what I do here is that I send a message to all processes. This is corresponding to the best ever broadcast. And I send my current proposal and my rank. Once I do that, I do a decide. And then we come to the following construction. So this code is only for the leader. And this code will be executed by every process. So let's understand this construct. A collect construct with a condition here from a specific process PR is false if and only if the failure detector P detects that that process has failed. Otherwise, it waits to receive the message from that process. So here's again, collect a value, x prime, from a process that broadcasted at round R. So this is very important, from process R. So you can see this, R is here and R is here. So it means you are only waiting for a certain message from a certain process. A message with this form, but from process R. It also means if you receive a message from another process, this will be buffered and not used until you explicitly ask for a message from that other process. So in case you get the broadcast, you basically adopt the value that have been delivered to you. You can see from this code, you will only decide in the round that you are a leader, and that's it. So this code is a little bit different from the event-based notation that we used before. In particular, the control-oriented code ensures proposals are adopted in a monotonically increasing order. So you will not collect a message, say from process 5, if you have not already collected a message from process 4 or detected the failure of process 4. That's what we mean by proposals are adopted in monotonically increasing order. So this is, of course, is regular consensus. Given this, if we just move the decision from here to this point, which would mean we are going to take a decision at the last round for all processes. Then we get a uniform consensus algorithm. So in the event-based notation, it means just do not decide until the last round. And we know this will work out because it's only processes that survive until the last round. These are the processes that are going to decide. All other processes will fail without deciding, and the processes in the last round will adopt the same value. Let us now look to an execution where instead of having a perfect failure detector, we have an inaccurate failure detector, which can suspect correct processes. So here is our scenario. P2 suspects P1 and P3 suspects P2. So P1 decides here. This is a regular consensus. P2 suspects P1, which would mean that P2 will move to the second round and decide on B. And P3 will move to the third round and decide on the value that it got at round 1, which is A in this case. So you can see here that in the case of regular consensus, if you use an inaccurate failure detector, you are not going to get an agreement. Processes are going to decide on different values. Now let us look to the algorithm with uniform consensus. So let us look at the execution where we have an inaccurate failure detector, but we have the uniform consensus algorithm, which decides on the last round. But we have the following inaccurate failure detector where P2 suspects P1, P3 suspects P2, and P1 suspects P3. So initially, P1 is going to propose the value A. This will be adopted by P3 because P3 does not suspect P1. But P2 is going to move to the next round and propose the value B. This will be adopted by P1 because, again, P1 adopts the one with the last proposer number, that's 2. But it will be skipped by P3 because P3 do not trust P2. And now P3 is going to decide on A. This was the last adopted value. But P1, which does not trust P3, is going to decide on B. So here you can see if we use an inaccurate failure detector, we will not be able to achieve consensus. The question that comes now is, can we use a weaker failure detector than P to solve the consensus problem?